Well, we are excited to be doing our first video using a non-beta version of HEC-RAS 6.0, which was just released this last weekend. This version has a lot of new features that we've been waiting for a long time. I'll be highlighting a few really cool ones in future videos, but in this one I wanted to first hit one that's still a limitation that hasn't quite been included yet. In this case, we're talking about depth varying roughness. I'll show you a little bypass or a workaround. I guess we can just call it what it is. It's a hack. If you've got a model that you set up like this one here, this is a rain on grid model. Once you've run the preprocessor, I'll turn on the geometry here so you can see the grids, and let's zoom in a little better so you can see some of the definition in the computational cells against the terrain. Now, once you've done this, you've got a couple of options, once you've got the preprocessor, in seeing the properties of each of these cells. So I can right-click on this one and show you the property tables for this particular cell or for any given cell edge. So if we want to look at these, let me go back to a couple of these properties here. I'll show you these just in the charts that I've right-clicked on and then printed out here. This is the profile along this face right here with this bund or berm coming up and down. All these things vary with elevation. So you see that elevation on the left, elevation on the left, elevation on the left, and then across here you've got different parameters. Of course, the area increases with elevation, the conveyance, the wetted perimeter, and then it looks very promising when you look here and try to get the property tables of the Manning's roughness. Hey, look, it says it varies with elevation as well. But as in previous versions, it's just a straight line. Now, there is some software out there that you can use for 2D modeling where each cell or each edge can be treated with a depth varying roughness. And in this case, we have elevation, but this could be depth over here. And you might have a diagonal line, or you might have some thresholds where it's constant up above or below those thresholds. Well, why would you want to do that? Why is that important? We've got a whole webinar covering roughness and another one covering rain on grid modeling. And I'd like to, put those together in this case and have a look at the adoption of roughness coefficients, where we're trying to accommodate sheet flow areas in rain on grid models like you see here, especially focusing on these areas where it's very shallow. So I'll put some links to those webinars down in the description below. But in the meantime, if you just Google sheet flow, here's the first image that comes up. And you can see sheet flow, I guess, in a very shallow area here. Well, what if we grid this and assume that this is your computational grid, have a look at the edges around here, and think about what's happening in a hydraulic model when we turn this into a computational grid around the outside with some LiDAR that we'll assume captures the undulations in the terrain here. What's actually happening inside the model? Well, if you picture HEC-RAS cutting cross sections around each of these edges and then try to move flow from cell to cell using the energy gradient between the cells and whatever roughness coefficient you've assigned, if your depths are, say, on the order of 1 meter or more deep, well, then sure, your typical roughness values might work. But what about cases where your flow is 1 centimeter deep? Or what if the depth is somewhere near the default display threshold in RASmapper, which is, I think, 1 millimeter? Well, and then picture what happens if you put vegetation on this, or if you make this steeper. If this sprouted into a field or into a paddock where it's all filled with grass, of course, the ground and then any vegetation on it would look a lot rougher to the shallow flows like this than it would to deeper flows. Now, if you have a look at some of the full momentum vodcasts that Chris and Ben have put together, we had one where I showed a way of varying the roughness with depth. And we talked about rain on grid modeling a little bit. I showed here just some of the toys that I use in teaching some of these things back when we used to have face-to-face classes. And then later in that episode, as we were talking about this, I showed a way of taking vector files and turning them into depth varying roughness layers. It's again a bit of a hack, but with that method that was included in that video, you'd have to export separate files for every single depth classification. Now, what's exciting about the new version of HEC-RAS is that we can do as many classifications as we'd like all at once using the raster calculator. So let's go back to a RASmapper here and I'll show you what I'm talking about. So let me zoom back out to where we were, and we'll have a look at some of the layers that we can now export and some of the parameters that we can put into the raster calculator. So I'll turn off the geometry, and I'll turn off particle tracing, and let's go to the max depth. So we're just looking at a kind of a static image of the maximum depth that ever got hit in this flood. So what we're going to do first is take this results layer, which I've already run here, and go and make a new calculated layer. And so we've got another tutorial where we step through some of the details of the raster calculator. And again, one of the exciting things about this is that you can share these scripts back and forth. So I'll show you where I've posted one of these scripts that I'm just going to copy and paste into this one. Now at this point there's only one script in here, and then I've linked to another one that I've done for flood hazard classifications, but this again can just be copied and pasted into your code calculation here. So let me start though by going to the, I'm going to keep this as user defined. We will add a layer into this one. I'll take the layer that I'm working on. This is the results file that I'm working on right now. I don't want the water surface elevation. I want the depth. Okay, I want this varying with depth, and so I'm going to classify the depth here based on the fixed profile at the max, and I'll call this D. So once I add this variable to it, I'll close it, and we get some information about how it's computed here, and we can see now that the depth is the layer that we get to operate on when we call out D in this code. So now going back to the script that I have online here, essentially all I'm doing is just separating the depth into different values. In my case, this is in SI units, so 2 meters deep, I'm going to call it a code of 1. 1 meter deep, so that's between 1 and 2, it's going to be a code of 2, etc. So if I come down here all the way down to the end if statement, and I just copy this whole cell, or this whole set of terms here, and paste it in, I can now check the code. It says it's compiled successfully. This is a little bit different than it was before with this new button here, but if you go on and have a look at the rest of the code, you can see some of the things that were added for you automatically. So with that, I'm going to go ahead and put it in my calculated layers folder, which is what it's looking for. I'm going to call this depth varying N, so dvar n with an underscore there. So I'll create that layer, and now you can see the layer right here. But if I want to actually see what this looks like, I'll go ahead and turn this on, and let me turn the terrain off so you can actually see it a little more clearly. Turn off my satellite imagery. Essentially, it doesn't have a legend that makes much sense yet, but you can see here that I've got different codes for each depth. Now, as I understand it, this is just a VRT file right now. It doesn't actually have a raster grid until we export this one as a raster. And so when I do that, it's going to ask me what layer I would like to use as a template. And this will then match the resolution and the extents of the template that you use. So I'm going to just use one that I've set up already as a template here. It's just one of my previous results layers that I've pulled in as a terrain so that I can get it to match. So I'm going to enter that name for the raster, call it dvarn, same as I've got for my for the layer up there. So now it's going to go ahead and export that. Sorry, that went on another window, so you can see here it was created. Now if I try to add this layer in that I've just made here, it's under calculated layers. And if I grab this one right here, which is the one I've just made, it does tell you the template file and which files this was based on when you made this layer. But I'm going to get an error when I try to pull it in that says we only support integer values for this. You know, if you're looking at the National Land Cover database and LCD codes, that's just an integer code that tells it what classification it has. It can't be 1.5 or 1.8. It has to be 1, 2, 21, 22, whatever that is. So we're going to need to have our raster in that format. Now there's a couple different ways we can do that. I'll show you one way in QGIS, and I think on that same website where I've got the scripts posted, I'll show you, I'll list a couple of other ways that might be a little simpler. I'm a longtime QGIS fan, and so I'll just show you how to do this using this one real quick. So all I've done here is to just open up QGIS and start a new project. What I'll do here is just drag in this raster file that we've got, And again, it looks like these are integers, but they are actually floating point decimals. We need to convert them into integers. So make sure that if you do this, that you launch it with GRAS and that you've got that GRAS loaded on the plugins. If that's the case, then when you just go to your processing toolbar, again, just by using that button there, you can just type in r.map and you'll get to this one right here, this script, which will then take as a raster whatever you want to do to it. You can operate on this one. In our case, we're just going to change it into an integer using that code right there. And I'll need to assign it a name here. Instead of a temporary file, we'll save it to a new file name. I'll put it right back under our calculated layers as d var n integer. So I'll just make sure I realize which one that is. And now when I run it, it might give me a couple little unsupported warnings here, but in the end, have a look at this. I've got an integer layer right there that I can then work with. So now that I've got this defined as an integer, we should be able to go in here into our map layers and this time do it without that error that we saw last time. So if I go here to create a new RAS layer, let's choose land cover layer. And now when we go to add this one, I'll go back to calculated layers and grab the one that we just created. And it's going to come up with this classification system here. Now, one thing you'll notice if you do this in QGIS is that the no data values, which you see here in yellow, are going to get the 255 value, like it's a color palette. One thing I wanted to show as well, though, typically no data values would be negative 9999, as you may have seen in some previous tutorials. I'll add one here, which I think I did in Global Mapper. You can see this one here then gets the negative 9999 as the name field. So what I'll do here is just go to surfacewater.biz/scripts, scroll down past the code there, and grab these values from the land cover data table, and I'll just take those and paste them in here under the classification. And to get these in the same order as the scripts in that on that website, just click on the name field to sort them. So when I paste those in, you might have to do these one at a time if you can't get it across the whole range. But you'll see here what these categories are going to be. Just to match some of my previous output, I'm going to change this to a raster gridded cell size of 5 meters by 5 meters. And I do want to define this one so that we can give it a name here and refer back to it later. And just to make it consistent with what I've done before here, I'm going to call it depth varying n, and we'll make that the land cover layer. So when I hit create, and again, this works very much like the when you import terrains, it's going to go ahead and make me a depth varying n layer that I can then associate with my geometry as soon as I've linked it up to n values. Now at this point, these are not n values. These are integer values that have coded it, and that's deliberate. Let's zoom in here on one of these areas, and we'll have a look here at what's going on. In essence, we've got now these codes that basically you can see the 2 there, and that tells us what the depth is, but it's not telling us what the associated n value is. So first we've got to right click on this and edit the land cover data table, because again, you might use this for something else other than roughness, and you can change them here universally without affecting the underlying source data. Now on that same website, surfacewater.biz/scripts, I've written in some dummy values here that you may or may not want to use. I'll just take these and put them into the same place here for each of these categories. And at this point, I'll just put in 100 for each of these values under percent impervious. We can have a look at that in another video. So with that, all I have to do is hit OK, and now see how it changed already. You can see as I'm hovering around here, the n value is now part of this code. Now there's one last step left. Let me zoom back out again, and let's have a look at where we are. I'll turn on a layer. This one, I think we had a 5 meter grid on it. I've got one where I did it all the way down to 1 meter, just to show how detailed you can get on this. So on the 1 meter land cover, again, I'll pull this up here. This is one I did previously, but it's got the same effect. It's just a bit higher resolution. So as I hover around here, you can see as my depth increases right here, I've got a lower N value, like a channel N value of 0.04. Here we got 0.05, 0.06, and then as we get out into the floodplain, we're a bit higher. And maybe that makes sense, but what happens out in this area here where we've got no data at all? And I did have an override on some of the no data values, but really what comes into your hydraulic calcs is the default value that's on your 2D perimeter. So if I right click on geometries and go to manage geometry associations, we need to make sure then that the appropriate Manning's N layer has been associated with the geometry that we're looking at. So I'm going to this geometry called NHEC, and I can use the one that we just did, dvarn. I'm just going to go with the 1 meter land cover here in this case. And once that's associated, then I can go back into my geometry and have a look here at the 2D flow area. And whatever my perimeter is, if I open this attribute table, I've got, if you've overridden the deeper areas, I want everything where rain falls out in here, where at the moment I've got maybe no data, but in the future I might run some rainfall over this and get something out here. I've got this one at a pretty high roughness value of 0.2. And you might even go higher than that. It sounds astronomically huge, but sometimes in rain on grid models, you do need values that high to mimic what's really going on in the shallow flow areas. Now, just to show that it's going to be an increase, I think I'll actually go in here and edit this one and change it to be something a little bit higher. So I think some of my other depths were coded to be 0.2, so I'll just change this to 0.3 just for now to distinguish that. So when I've got that in there, one of the last things you can then do to check, we'll stop editing that and apply it everywhere, is to go down here under your geometry and turn on Manning's N. And let's see what we've got here. So this is our final result, and this is always what you ought to check in the end before running a model. I've got a whole bunch of classification layers here showing me what these different categories are, and showing high N values being red and low N values being light blue. So as I kind of zoom out on that, let me just turn off the geometry here so it's a little more clear. As I hover around here, you can see again channel values coming out, and in some of these areas I think we'll step through all of the categories on our way from the deeper flows out here into the overbanks, where we get up into the no data values, which will end up being very rough, because that's what's going on out there is sheet flow, and the sheet flow is going to have roughness elements that are very significant relative to the depth of flow. Now remember, the depths that we used here initially to classify this thing were based on the initial roughness, which was uniform. So if you really wanted to get this right, you might run through the process another time or two just to get convergence of the results. And also need to keep in mind how this changes over time. So I might just cut a cross section and you can see what's going on here and think about whether this makes sense. So with my profile line here, I'll just cut one going from left to right, looking downstream, and I'll call this check section, and we'll just have a look at this and see what the water surface elevation looks like over time. So I'll turn on the maximum flow depth here and as a water surface elevation, and let's just have a look at this, and we'll plot this on a time series. So here it is. If I come in from 0 as the storm starts arriving and I've got some of this sheet flow, again, think about how this happens over time. Okay, you might have a different roughness value here at this time step than you would up at this time step. So, maybe we ought to, have true roughness, depth varying roughness over the entire hydrograph. So this is more helpful. The method that I've shown you right now is more helpful if you're interested in a flow rate that stays relatively constant over time. It's almost like a steady flow. If it is flashy and there's lots of storage areas that might be influenced by overflows that are really sensitive to the roughness as that flow arrives, you might still be missing the mark. If this didn't flow over here because this was smooth or this was rough or whatever it was, that's where models that can do this at every time step might be better suited for that sort of an application. And I also wanted to highlight that in some cases, we end up tweaking the roughness coefficients to try to better reflect the timing of hydrographs or even the peak flow rates or the volumes inside of a hydrograph. So if I plot a flow hydrograph along that same section that we're looking at, I've run this with different roughness values, yeah, you've got to be a bit careful about what's really going on. If you had real world measurements out here, or you had a rainfall runoff model and you're trying to match that, in some cases you're slowing down the flow and getting less flow in the system, but then that flow is higher because of the higher roughness. So that's where this depth varying roughness can come in handy. But be careful what's really going on. If what was making it flow down, in this area, maybe what's influencing that is the, some interflows or something like that. If you are trying to manipulate overland flow to try to behave like interflow, it's really hard to match all three things at once. The timing of the peak flow rate, and the volume under that curve all in the same model run. That's pretty tough to do. So we've got to still acknowledge the limitations of the model. So I hope you've enjoyed that and that you're having fun playing around with the new features here. We're going to be rerunning all of our training courses for HEC-RAS using 6.0. I'll include some of the links to those courses that cover the essentials. Chris and Ben have a more comprehensive course that comes along periodically as well, so stay tuned for that. If you are interested in more details on scripting, we've got Python courses and QGIS courses specifically for water modelers. If you are interested in those, I'll include those links as well. So yeah, stay tuned for more. Thanks for subscribing, and we will see you next time.